This video will cover dehydration reactions of alcohols. There are actually two different types of dehydration reactions of alcohols, but they're related and the two compete, so we will discuss them together. The first of these is dehydration of alcohols to form alkenes. This is a reaction we've learned about before, so this is just review. If we treat an alcohol with sulfuric acid and heat it up, the alcohol will eliminate to form the alkene. The reaction is called a dehydration because it loses water. The mechanism of this reaction is an E1 mechanism. In the first step, we protonate the alcohol. This turns the alcohol into a good leaving group. Next, the leaving group leaves, forming the carbocation. In the final step, the water that was just formed deprotonates the carbocation to form the alkene. There are a few things to keep in mind when thinking about the dehydration of alcohols to form alkenes. First of all, as mentioned before, this is an E1 mechanism. This means that a carbocation is formed, and therefore carbocation rearrangements are possible. Additionally, because it forms a carbocation, secondary and tertiary alcohols work best. Primary alcohols typically do not undergo dehydrations because the primary carbocation is too unstable. Finally, remember that if there are choices in terms of regiochemistry for the alkene product, Zaitsev's rule will predict the proper regiochemistry. The most substituted alkene will predominate because it is most stable. The other dehydration reaction that we will discuss is called condensation. In particular, this is condensation of an alcohol to form ethers. In this reaction, the alcohol is treated with sulfuric acid and heat. Two molecules of alcohol come together to form the ether, with a loss of water. This is called a condensation reaction because it involves two molecules coming together with a loss of water. The mechanism of this reaction is similar to the mechanism for dehydration. The first step is protonation of the alcohol. Once again, this turns the hydroxy group into a good leaving group. The protonated alcohol then reacts with a second molecule of alcohol. This step is an SN2-like mechanism, where the alcohol attacks, kicking off water as a leaving group. This forms the protonated ether. In the final step, the water that was just formed deprotonates to form the ether. It is important to note that this reaction only works in the formation of symmetrical ethers. We can see why this is so if we try to set up the reaction with two different alcohols. If we try to carry out a condensation reaction with alcohols with two different R groups, R1 and R2, we will get a mixture of products. Two molecules of R1 could come together to form this ether, or two molecules of R2 could come together, or one molecule of R1 and one of R2 could come together. Therefore, the condensation of alcohols to form ethers is only a useful synthetic reaction when the alcohols are the same and the ether formed is symmetrical. Now let's compare the condensation and dehydration reactions. If we compare these two reactions side by side, the reaction conditions look almost identical. However, these two reactions result in different products. The main difference is that a dehydration uses one molecule of alcohol starting material per molecule of product formed, whereas condensation requires two molecules of alcohol to form one molecule of product. We can control which of these reactions happen by controlling the temperature at which the reaction is carried out. A higher temperature favors the dehydration reaction. Typically, we see dehydration occur at temperatures above 180 degrees Celsius. Condensation is favored at temperatures of less than 140 degrees Celsius. The reason for this difference is an entropic one. Dehydration has a larger, more positive delta S, or change in entropy. In other words, dehydration has a more favorable entropy change. Remember that entropy is somewhat like disorder, and the dehydration reaction involves one molecule of reactant forming into two molecules of product. This leads to an increase in disorder of the system. In other words, a positive change in entropy. Condensation has a delta S, a change in entropy that is close to zero. This is because the condensation reaction takes two molecules of reactant for two molecules of product, causing very little change in disorder. In other words, a change in entropy close to zero. Remember that when we're talking about the favorability of a reaction, in other words, whether dehydration or condensation is favored, we're talking about the change in Gibbs free energy. Remember that when delta G for a process is less than zero, the process is favorable and occurs spontaneously. When the change in Gibbs free energy is greater than zero, the process is unfavorable and will not occur spontaneously. Also remember the equation for calculating Gibbs free energy. The Gibbs free energy is equal to the change in enthalpy, delta H, minus the temperature times the change in energy. In order to make delta G favorable or negative, we need delta S to be large and positive. In addition to this, increasing the temperature does a few things. It makes the term negative T delta S more favorable as the temperature gets larger. As temperature increases, the negative of negative T delta S becomes larger and more negative, making delta G larger and more negative. In addition, increasing the temperature makes the term T delta S more important to the overall value of delta G. In other words, as the temperature increases, the size of the change in entropy becomes more important than the size in the change in enthalpy. This explains why dehydration becomes more favorable when the temperature increases. Remember that dehydration has a favorable, positive change in entropy, while condensation has a delta S close to zero. Therefore, as we increase the temperature, the positive entropy change for dehydration becomes more important, making this reaction favored over condensation.